want to show that it's true for n equals to 5. Step 2, our assumption. Step 3 is our proving, where we show it is true for n equals to k plus 1. Okay, so we just went through with basic induction using inequalities. This is a new method that I want to teach you. It's called using the difference within this inequalities. How we use this is, let's consider if we want to prove that the left-hand side A is greater than the right-hand side B. Can you imagine that if we move B to the other side, A minus B is greater than 0, which means that if we use a difference between them, as long as we can find out that this number is positive, then we can say that yes, A must be greater than B. And it doesn't matter if it's B or A, as long as you follow this general sign, prove whether it's positive or sometimes you'll be proving it's negative, then you can show that this is greater than the other side. So this is a really good method to have on hand, because sometimes with these inductions, you can get a little bit lost and not know exactly where to start. So if that does occur, you always know that you can use using the difference for your inductions with inequalities. Okay, let's apply that to a real question now. So question 2, we want to prove by mathematical induction that n squared is less than 2 to the power of n, and it's for n is greater or equal to 5. So starting off with step 1, we want to show that it's true for n equals to 5. So remember, we just take the smallest value of this. And left-hand side, 5 squared is 25. Right-hand side, 2 to the power of 5 is 32. So we can definitely conclude from that yes, the left-hand side is less than the right-hand side. So therefore, this statement is true for n equals to 5. All right, step 2, our assumption. Assume it is true for n equals to k. So we just substitute in k. K squared is less than 2 to the power of k, for k is greater than 5. Step 3 is our proving, where we show it is true for n equals to k plus 1. So substituting in k plus 1 here, I have k plus 1 squared, and over here I have 2 to the power of k plus 1. So this is what I want to prove. This inequality is what I want to prove, that the left-hand side is less than the right-hand side. And now we're going to use a method of using the difference. So we're going to have the right-hand side minus the left-hand side. So let's do that, subtract that. So to prove that if this side is greater than that, we want to show it's positive, don't we? So we have 2 to the power of k plus 1 minus k plus 1 squared. And we can just change this into 2 times 2 to the power of k. And this I've just expanded to k squared plus 2k plus 1. Let's use our assumption in step 2, which is that 2 to the power of k is greater than k squared. So here I have 2 to the power of k. And over here, I've put in k squared. We've said that this side is greater than that other side. Therefore, this side must be greater than that. If I've put in, can you see how everything else is exactly the same, right? 2 is the same. This and this is exactly the same. The only thing I've changed is this becomes the lesser value of k squared. So therefore, this must be less than that. Does that make sense? If I've only changed one thing and that one thing is less than, then this side must be less than the other side. So using the assumption, we've done that. So now what we need to do is to simplify some of these things. So over here, we have 2 times k squared minus all of that. And I just want to simplify, just working with this bit over here now, okay? So we have 2k squared minus k squared minus 2k minus 1. And that's how we get k squared minus 2k minus 1. Now that will also become, I want to make a perfect square there. And how I do that is you go k squared minus 2k. And remember, you take half of this, which is -1, and then we want to multiply that by itself, which becomes +1. Now we can't just go around changing the equation, so we want to subtract 2, so that becomes the same as that equation. Now this k squared minus 2k plus 1 becomes a perfect square of k minus 1 squared, and that's where we get the negative 2. So now we've changed it to that, k minus 1 squared minus 2. Let's look back to our equation that we're actually working with. We have k plus 1 squared is less than 2 to the power of k plus 1. So now we've shown that this is this over here, but we're using the difference. Now remember what I said about the difference is if we're going to go this side minus that side and that's greater than, then what we want to prove is that the right hand side minus the left hand side is greater than 0 or positive. That's what we want to do, isn't it? This here is a perfect square. Let's consider that this is greater or equal to 5. So since its k is greater or equal to 5, substituting in 5, what do we have here? We will have 5 minus 1, which is 4. 4 squared 16, 16 minus 2. So the smallest number it can be will be 14. Therefore, this will always be positive, won't it? So we can say that it will always be greater than 0. This is always greater than 0, we can say that the right-hand side minus the left-hand side is greater than 0. Because this is all equal to, this is greater than, this greater than, we've proved that this is greater than 0. Now moving that to the other side, we've proven that right-hand side is greater than left-hand side. Just move that to that side. Therefore, the left-hand side is less than the right-hand side, which is what we wanted to show originally. So therefore, this is true for n equals to k plus 1. And in our conclusion, we can just write, therefore, for n squared less than 2 to the power of n, it is true for all integers of n is greater than 5. So remember, when we're using the difference method, what we want to think about is what we want to prove at the end, because it's easy to lose track of that. So here, because we're doing right-hand side minus left-hand side, I would actually just write that at the top of your page. It's greater than 0. So what I'm trying to prove is that it's positive. So when you get to here, you don't forget what you're trying to do. You can remember, okay, I'm trying to prove it's positive. So since this is the smallest number it can be 16, then the smallest number the whole thing can be is 14. So yes, it must be positive.